Welcome to the Explainer. Okay, today our goal is ambitious, but honestly, it's totally achievable. We are going to demystify the magic behind modern artificial intelligence, and we're going to do it without getting lost in pages of university-level calculus. We hear about AI constantly, right? But today, let's actually look under the hood. By the time we wrap up, you'll have a rock-solid conceptual grasp of the actual building blocks powering this incredible tech.
Okay, let's dive into this. Section 1, the AI revolution. Before we get into the microscopic math, we really need to take a second to appreciate the jaw-dropping pace of artificial intelligence today. I mean, it is so easy to become desensitized to it all, but just consider where we were a mere decade ago. In 2015, the absolute state-of-the-art AI was generating these blurry, distorted facial images. Fast forward to 2020, and we leaped into generating full videos. Then late 2022 and 2023 hit us with ChatGPT and GPT-4, massive, world-changing leaps in capability that totally pushed the boundaries of what computers could do with natural language. And today, well, we aren't just running giant models in massive million-dollar data centers anymore. We are literally running extremely powerful, multimodal models natively on edge devices, like right on your phone. And this brings us to a true wow moment for the AI community. You see, the gap between those massive cloud models and small on-device models used to be enormous. But recently, an open-source model with only 2 billion parameters, which basically means anybody can download it and run it on their phone, actually started beating the original GPT-4 across almost every single benchmark. It's a real game changer.
0. That is exactly the number of internet connections you need to run these new models. 0 Wi-Fi. You can put your phone on airplane mode, go entirely offline, and ask an AI complex math problems, like finding the zeros in the modulo 7 finite space, and it instantly knows the answer. Even wilder, we now have end-to-end audio models that take audio directly in and output audio directly back, no converting to text in the middle. That means zero latency and no loss of emotion. The model actually detects the emotion in your voice and responds in kind. It is an absolutely remarkable shift in capability.
All right, let's move on to Section 2, decoding deep learning. So how on earth is this actually happening? Let's peel the onion back a bit and decode the terminology, kind of like a funnel. Step 1 at the very top is artificial intelligence. At its core, that just means building algorithms to process information to inform future decisions. Step 2, we narrow down to machine learning. This is a subset of AI where, instead of explicitly programming a computer with all the rules, it actually learns those rules from data. And step 3, at the very bottom of our funnel, is deep learning. This is a highly specific subset of machine learning that utilizes deep neural networks to extract features directly from raw data in a hierarchical way.
Now here's a crazy fact. The fundamental building blocks of these deep learning algorithms aren't actually new. Some of them have been around since the 1950s. So why is deep learning completely taking over the world right now? Well, it comes down to 3 main pillars. First up, big data. The world just has an unprecedented abundance of data for these algorithms to feed on today. Second, hardware, specifically GPUs that have drastically accelerated parallel computing. And third, software. We now have democratized frameworks like TensorFlow and PyTorch that let developers create, train, and deploy these models super efficiently.
Which brings us to Section 3, the single neuron.
Let's zoom all the way in, like microscopic level, to the absolute foundation of AI. We are going to demystify the core mathematical building block of every massive model out there, the single neuron, also known as a perceptron. It breaks down into 3 very digestible steps. Step 1, compute the dot product. That just means you multiply every input by a corresponding weight and add them all up. Step 2, add a little mathematical constant called a bias to help shift the result. And step 3, pass that final number through a nonlinear activation function. Multiply, add, and activate. That's the whole shebang. But hold on, why do we even need that third step? Well, real-life data is messy and highly complex. Imagine a graph with a bunch of red and green dots all mixed together, and you're trying to draw a single straight line with a ruler to perfectly separate the colors. It just doesn't work, right? A nonlinear function, like the sigmoid function, basically takes away that straight ruler and gives the model a flexible pen. It provides the mathematical power to draw curved decision boundaries, which is absolutely crucial for modeling complex, real-world data. Moving right along to Section 4, building the network. Now that we've got our single neuron, let's look at how we actually stack these microscopic blocks together. A deep neural network is created by stacking multiple linear, fully connected layers with those nonlinearities squeezed right between them.
By passing raw data through deeper and deeper layers, the network slowly builds hierarchical representations. So the first layer might look at an image and just detect basic lines and edges. The next layer combines those edges to find curves and corners. And the deeper layers combine those corners to recognize specific features until the final layer accurately detects, say, a complete human face. It's like a giant puzzle coming together piece by piece.
Section 5, Training the Machine.
Okay, so we have all of these stacked layers of math, but here is the million-dollar question. How do they actually learn to give us the right answers? Let's ground this abstract concept of training with a scenario we can all relate to. Imagine we build a neural network to answer a simple yes or no question. Will you pass this class? And let's say our inputs are simply the number of lectures you attended and the hours you spent studying. Let's say you attended 4 lectures and studied for 5 hours. We feed those numbers into our network, so you pass your numbers in, and the network predicts you only have a 10% chance of passing. But looking at the historical ground truth data, it shows that students with those exact numbers actually pass 100% of the time. So why was the network so horribly wrong? Because right now, a randomly initialized network is essentially a brand new baby making wild, random guesses. The difference between the model's terrible prediction and the ground truth reality is called the loss. Loss is simply the mathematical measurement of how wrong the network's guesses. And our main goal, we want to minimize that loss.
To minimize that loss, we use a brilliant algorithm called gradient descent. Picture this. The loss landscape is like a massive hilly valley, and you are trying to walk down to the absolute lowest point at the bottom. But here's the catch. You're blindfolded in the pitch dark. How do you get to the bottom? Well, you feel the slope of the ground under your feet. That slope is the gradient, and you take a small step downward in the opposite direction of the slope. You just repeat that until you find the lowest error. Modern developers even use adaptive optimizers, like one called Atom, which cleverly adjusts your step size or your learning rate so you don't get stuck in a shallow ditch or completely overshoot the valley floor.
But how exactly does the network figure out that slope when we're talking about billions of parameters? Well, that happens through a process known as backpropagation. It applies the mathematical chain rule to pass the error gradient from the final output all the way backward through the entire network. This is literally how the network signals every single individual neuron exactly how it needs to adjust its specific weight to get the answer right the next time around. Now, calculating this error for every single piece of data simultaneously, that is computationally massive. On the other hand, vanilla stochastic gradient descent computes the gradient on just one single random data point at a time, which is fast for sure, but it's erratic and super noisy. So the solution is mini-batching. Developers compute the gradient on a small chunk of data, say 32 points at a time. It's a really smart middle ground that balances speed with accuracy, letting the model efficiently navigate that high-dimensional loss landscape without checking the entire dataset every single step. And finally, Section 6, Preventing Overfitting. So, we've built our model, we've trained it, but we have one final, absolutely crucial challenge: making sure it actually understands the real world rather than just memorizing a textbook. This is essentially the Goldilocks problem of machine learning. On one side, you have underfitting. The model is too simple, kind of like trying to use that straight ruler for curved data. It just misses the intricacies. But on the other extreme, you have overfitting. This is a model that is so complex, it perfectly memorizes every tiny bit of noise in the training data. The problem? The second you deploy it in the real world on data it hasn't seen before, it completely fails to generalize. We want our model to be just right. To make sure our model is just right, we use what are called regularization techniques. Take dropout, for instance. During training, we literally randomly kill 50% of the neuron activations in every batch. I know it sounds totally counterintuitive, but by shutting down random pathways, we force the network not to rely on any single memorized path. It forces the model to learn deep, resilient, alternative understandings of the data. Another awesome trick is early stopping. We continuously monitor the model on a totally separate testing dataset. And the precise moment the model starts doing worse on that testing data, even if its training scores are still going up, we hit the brakes. We stop training right there because we know it has crossed the line from true comprehension into just memorizing the noise. Wow, we have covered an immense amount of ground today. From the macro AI revolution down to the math of a single neuron, through gradient descent and all the way to dropout regularization. We now genuinely understand the foundations of how machines learn from raw data. But, this leads to a final, really provocative thought. Everything we looked at today was largely about static data. Armed with these deep learning building blocks, how will we adapt them to conquer sequence models? How do we handle things that unfold over time, like reading a paragraph of text, listening to continuous audio, or processing frames of a video? How do large language models actually process the sequence of time? That is the fascinating frontier of sequential data, and exactly what we should be eager to explore next. Thank you so much for joining me on The Explainer.